Welcome back to another video of our course Measure Theory for Probabilists. Today and in the next videos we are entering the last section of the manuscript, which is product spaces. They are very important in probability theory when it comes to stochastic processes, and they are usually not covered as deeply in other measure theory courses. That's why they're important for us here. Today we start off with, again, sigma algebras, but this time on product spaces, and we will have a special focus on arbitrary index sets, and I will explain to you in a second what that means. So let's get started. We have product spaces, and again we need sigma algebras in order to do measure theory. So first of all, what's a product space? Okay, that's something you might know. There's this cross product or Cartesian product of the spaces omega I, and that's just the vector, and the index set is here. So for example, if I would be finite, you would write something like, I don't know, omega 1 until omega n, then the I here would have n elements. Okay, that's a product space. And every time you have such a product space, you can have projections. For example, I could project this vector here down to the first component. So that would be the map, which maps this one here to omega 1. And more generally, if you have the full index set, a subset of it, and another subset of that subset here, you have a projection, which means you take vectors indexed with j and you just leave out all entries which are not in h. Then you get this map here, that's a projection. We will need them. And if the j here is the full index set, so if that's I here, we leave that away. And if h here is just a singleton, we'll write that like this here. And I think that's usual notation. So first, we had that sigma algebras are usually constructed from topologies. That's where we had the Borel sigma algebra. So we had, if O is a topology and sigma of O, that's the sigma algebra generated by the topology, that's what we usually then called the Borel sigma algebra on our space omega. So we again here have to start off with a topology, and which topology are we going to take on the product space? Assume we have the topologies here on the single spaces. What is then the topology on the product space? And there's one concept here which we had briefly. So O of C, so that's the topology generated by a set system. So I want to define a topology, and I'm doing this by giving a C and the topology generated from this here. And that's as with sigma algebras. So this here is defined as the intersection of all O prime, let's call them. C is subset of O prime, and O prime is a topology. So that's the topology generated by this here. So that's done as for sigma algebras. Just make the intersection of all topologies which are bigger than C. But what's our C now for the product spaces? And recall that we have all the single, so the elements of the product, we have topologies here. So we can take AIs from OI. We can make this here as one coordinate, and all the other coordinates are the full space. That's a set system C, which is a set system on the product. And we say the topology is the topology generated by the C here. And for defining the C, we just need the topologies on the elements. And one remark, which is also important, the PIs, so the projections, they are continuous with respect to this topology. Recall that if you have a map F from omega to omega prime to topological spaces, that's continuous if and only if, I write it very briefly like this, f to the power of minus 1 of O prime, so that's the topology on omega prime, that's subset of O, which means the pre-image of every open set is open. So that's what this says here. And that's one definition of continuity, which you might have heard of. And that's very easy to check here for this claim. Projections are continuous. I have to have an open set in O prime. So what's O prime here? So the PIs, they go from the full set, let's call this omega, to omega I. And omega I has the topology OI, and the pre-image of the projection on AI, that's AI, cross product with all the omega J's, which are the full set. And apparently, this here is of this form, which means this here is in C, and C is subset of O, because O is always bigger than the set system it generates. So that's a very brief proof that projections are continuous. Okay, now we know what the product topology is, but we are going to also need the product sigma algebra. And it turns out there can be two versions. And maybe I make it like this here, using some nicer color, like this. It's important here to know. So here's some difference. So I will define two sigma algebras, and one is always subset of the other. So this here is always subset of this here. And if some things are met, then I have equality. Yeah. So that's the structure which is important here. So what are the two possibilities? I can construct a sigma algebra on my omega. First, you could say, well, okay, I have a topology, and I know that topologies generate sigma algebras, like this here. I just take the borrowed sigma algebra on the product, using the product topology. And that's this here, B of omega. So that's this one here, that's the bigger one. And there's another one, which is maybe smaller. And that's this one here. Because you can also do this, the following. You can say, I do the same thing as before. So we had the C here. I have an AI across all full spaces. I do the same thing here, but I do that for AIs which are in Fi. In Fi are these here. And for the sake of what we're going to have here, Fi could be B of omega I. So the borrowed sigma algebra using the topology which I have on omega I. And I generate a sigma algebra from this here. So it's just generated by these here. But that's something different than using the product sigma algebra. And this here will be the better sigma algebra, and we'll call this the product sigma algebra on omega. So let's come to the most important thing here, which is this lemma. And one important thing is I here is arbitrary, which means it could be, for example, I equals the full interval from 0 to infinity. And that's something which is very common in probability theory, because one product space is just a function space. Let's say all omega i's are maybe R. Could be the case, or all omega i's are R. And a product of R using this index set, so that's just all functions from 0 infinity to R. And if you want to have random functions, so what are these? They're called stochastic processes, because what you draw when you have stochastic processes is something like this here. It's t maybe, that's called as xt, and something which fluctuates around. And here for every t, you have a random variable, which should then have a distribution. And I want to have a distribution on all these functions here. That's exactly what you have here when you have an uncountable infinite index set. And here the omega i's, they are somewhat nice. So this arbitrary I is something which is not unusual in probability theory, not at all, but which complicates things a bit. Because here we see we only have subsets here. But if I is countable and, okay, the spaces are nice, then you have equality, but only then. But if I is uncountable, you will never have this. So, okay, that's not so hard to prove, actually. But okay, one thing. Let's look at this here first. Let's look at the left-hand side. I'm generating the sigma algebra from this set, and this set here differs from the full set only at one coordinate. And generating a sigma algebra, okay, you can make countable intersections, for example, or countable unions, but everything is just countable. But when you do this, what you end up with, there are always sets which differ from the full set only at an at most countable index set. So this sigma algebra consists of sets which differ from the full set only at a countable number of indices. Whereas that's not so clear for the other sigma algebra, B of omega, because here you have the topology generated from this set here. But when you generate a topology, there's not this restriction of something is only countable. You can have arbitrary unions, or for closed sets, arbitrary intersections in order to have something closed. And from this, then you generate the sigma algebra B of omega. But this here might also contain sets which differ from the full set at all or at uncountably many indices. That's one reason for the subset here. So this here might then contain more sets than this here. But of course, if I is countable, then, well, it doesn't matter if you only allow for countable numbers of differences from the whole space or uncountable, because there are no more than countable, and then it could be that these two are the same. So that's just for the imagination. And the proof here is actually simple. you need these three things here. So C is a subset of the topology generated by C because the topology generated by something is always bigger than something. C is subset of E. Okay, why is that? C has here only the open sets, and E has here the measurable sets, but they were generated from the open sets, so C subset of E. And finally, E is subset of sigma of C, so these measurable functions, they were generated by the open functions. And when you have sigma of C, you in particular also generate these here. So if you have something like this here, you can also generate them using these functions. So that's the reason for E is subset of sigma of C. And now you write this here. So this product sigma algebra is by definition sigma of E. Sigma of E is the same as sigma of C because on the one hand, here you have this relation. That means sigma of C is also subset of sigma of E. On the other hand, sigma of E is subset of sigma of C, which is sigma of C. That's the other direction. So you have this here. C is subset of O of C, which means sigma of C is subset of sigma of O of C. And that was called the Borel sigma algebra. So you only have here, you have a subset relation. But if I is countable and all spaces are separable, which means you have a dense set, a countable dense set within every omega, that means if you have an open set, you can write as a countable unions of sets in C, which means the topology generated by C is subset of sigma of C. So every open set is measurable. And then you see, well, you can write sigma of O of C, this here, is subset of sigma of C, which is sigma of C, which means this relation here also works the other way around, which means you have equality here, and then the result here follows. Okay. So that was this here. And, well, you remember we also had generators for sigma algebras, and that's what comes here. We used to work with semi-rings, and that's not different here for the product spaces. And there's a general thing here which we will use for semi-rings. So here the first is for finite index set. So if you have semi-rings on all indices and you make the set system of all products of elements in the semi-ring, then you end up having a semi-ring again. And I'm not going to prove this. You can look that up in the manuscript, but I'm drawing one picture. And the picture goes like this. So with an index set of, so I equals 2, you have 2 coordinates. And this set here is one such a product, and that here is another such a product. And you see two things here in this figure. First, the intersection is again a rectangle. So it's again of this form here, which means H is cap stable. It's intersection stable. And the other thing is, let me take a different color. If you have the set difference of these two, like this here, the first one minus the second, you have this one here, which is not of this form here. But as the semi-ring only requires, you can split it up here, like this, for example. And you can write down the yellow area as the left thing here and the right thing. and both of them are of this form. The requirement for semi-ring is only that these set differences can be written as a disjoint union of elements of this type. And as you see, that's the case. Okay. So if you have semi-rings, you also have a semi-ring on the product. And the second thing is, I is here arbitrary, HI is cap stable, and a generator of Fi. Then the set system consisting of all elements which are just products over AIs here in the generator, and all the rest gets the full space. That's again an intersection stable generator of the product sigma algebra. We also need that. Just as an example, on RD, that's certainly an important thing. I have the notation here, A is a vector, B is a vector, and I have the interval between vectors. And what I mean by this, so all entries in A have to be smaller than entries in B or equal. Then that's only just the product of intervals, where we write the entries of A and entries of B here. Then this here is a semi-ring and generates the full sigma algebra. Because all these elements here, say half open intervals, say they generate the sigma algebra on R. They're cap stable, and they then form, like this here, an intersection stable generator of B of R. And they are also semi-rings. Yeah, so the proof is a one-liner here. H is a semi-ring that generates the sigma algebra you're interested in, and use this lemma here. Okay, that's it for today. Next time we will start with constructing measures on these product spaces and see if we can also say something about integrals. See you then.